Swayam Prabha. Digital India. Educated India.
So before I get started, I just wanted to get a sense of the topics which were covered today. So what topics were covered today since the morning? Like particular topics, like you had like 3-4 lectures before this, right? Like what were the topics that were covered? Huh? Okay. 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 Uh-huh. Okay. So this will be it'll not be like too technical, but also at the same time not like a super high level talk. We'll actually get to some concrete problem because I assume that because this is like in the middle of the day already you saw some introduction to AI and so on. So we'll get to a concrete problem. Okay, so today the topic we'll be discussing is this: how do you teach AI systems, especially when labels are expensive? So a bunch of the topics which are covered will be clustering, diversity, topic modeling, and learning under a budget. So in general, data may be abundant, but good labels are often scarce. So this is like a example. Suppose you have 10,000 data points. Now data points here are very generic. They can be either some photos or some audio clips or some videos or text, anything. You just have some data, but all of this data is not labeled. So I don't know if you've seen since the morning. So in machine learning, there are two major types of algorithms which we look at. One is called unsupervised learning algorithms, and then you have supervised learning. So data is of two forms. One is this unlabeled, where you just have the raw text or raw images. Then you also have some labels for that. So thing is, like if you have like let's say 100 photos, then just the photos would be unlabeled data. But along with the photos, if some human is looking at the photos and then also assigning some information, let's say there are like 5 different options for the humans to label them as, like cat, dog, ship, uh, and like usually if you use if you try to search for something on Google, it'll also give you like this captcha, right? So in captcha it will give you some photos and it'll ask like, okay, can you identify which of these are belonging to a bridge or something. So the human who is working there, they are assigning labels, whereas the data is a raw data. Okay, so if you have so getting this unlabeled examples is relatively cheap. So there are a lot of like public data sources. Like if you take some newspapers or if you take like YouTube videos, then there's a lot of data already. Like you have like thousands of gigabytes, thousands of gigabytes of worth of data, which is already present. But if you want to use it for any particular application, let's say if you want to develop some medical application where a doctor is looking at some images, not a doctor, like your AI model is looking at some images and it wants to classify whether they are cancerous or benign, then to develop that model, you will need not just this raw data, but you'll also need data which has been labeled by a expert, which is a expert doctor. So a doctor's time is very expensive. So therefore, even if you have like a lot of data, you cannot like have them sit and keep labeling all the entire data points, because a doctor has to look at one image and then they'll take like 1 minute or 2 minutes or whatever. And if they have to do it for like a lot of examples, then their entire day will be gone. But they also have other duties which are their primary functions, like taking care of patients and so on. Okay, so the goal here which we want to look at is if you have a lot of such data, then among this data, which data should you select for labeling basically. And to do this, we'll use some mathematical concepts. So we'll use the notion of vectors, distances, averages, objectives, and some algorithms. Yeah. Yes, correct. So there will be some predefined set of classes. So in the case of this cancer, non-cancer thing, if doctor has access to, let's say, some type of image, like some MRI scan or some type of, I'm not a medical expert, but anyway, if there are some images, getting that is relatively cheap because a patient can go to like a scanning machine, and for that one patient, the machine will generate like lots of images. Whereas if you want a doctor to go to each of them, it might be expensive. And you can actually get a relatively cheap data set by just recruiting a lot of people on the road. You can just go and like find a cohort of like say 100 patients. You can send them to, not necessarily patients, 100 people, and you can send them to these machines and get data. But if you want your doctor to actually sit and like label whether this is like cancerous or non-cancerous or something, then it will be expensive. Yeah. But label is basically that, like you assign one class, the class can be anything. It can either be like this or it can be cat, dog, whatever. I mean, essentially you want to teach an AI model. So this teaching is done by this labels. Okay. So some examples. So doctor labels medical scans. A biologist will annotate cells, like even cells also, like some of them can be cancerous, non-cancerous, or different types of cells. And linguist will label like speech. If you have like bunch of different speech patterns, and what is a different categories you can fall into. Yes, unlabeled data is cheap, whereas human labels are expensive, and models need useful examples. So the question is not only how much data, but also which data is it. So this is like a real practical problem. Like we are here at IIT Madras, we are working on developing a lot of machine learning models, and often the pipeline is initially we get like this large chunk of data somewhere, like you either generate it synthetically or you collect it from YouTube or you collect it from some newspapers or something. But then we actually have to send it to human annotators, and this involves a cost. So we work with multiple vendors, and then we have to like get some quotations. So they will tell that, okay, like for reading this 5 different newspaper articles, I will charge you like, let's say 100 rupees. So when you want to scale it to like, let's say 10,000 or 1 lakh, then the cost will significantly go up, like 10 lakhs, 50 lakhs, whatever. So this is an important problem. Okay, so basically you want to select a subset of this data, and if you select it very badly, then this will waste a lot of your budget. So for example, if you look at this data, data itself is usually high dimensional. So it will be, it cannot be represented easily on like a 2D plane, but there is something known as dimension reduction, where you can take high dimensional data and map it onto a 2D space. So each of these data points will correspond to some actual data point. Like each of them can correspond to one image or video or newspaper article or text, like a book or something. So if you, and the key way, like how we transform them into this data, we are not discussing right now, but assume that there is a way in which you can transform, with the constraint that eventually in this transformed space, if you look at 2 data points which are close to each other, then even the original data will also be somewhat similar to each other. So for example, if your data has images of both cats and dogs, then once you transform it into this space, the images which are close to each other will be like just cats, or even among the cats, the images which will be closer to each other will be like the same breed of cat, or like the more similar the images, the closer they will be. And if you have such a data, and if you select, let's say, all the points from this one cluster, then a lot of it is redundant. If you get like one cat and then get some label for that, then other images which are very similar to that, you don't get as much information by getting them. So there are 3 common failure modes. One is this redundancy. So you see near duplicates. Even if you extract like YouTube videos, you might see like a lot of videos which are very similar to each other. And then there is also this other problem, which is blind spots. So if you look at like this particular thing, it's like one case, but it's rare. So the density is much lower, but this can actually be very important. Like if you look at the case of doctors who are labeling, then actually the rare cases might be the patients who actually have some type of disease. So you don't want to throw them away. it's actually important that you also capture the rare cases. And then other thing which at responsible AI, which we care about more, is ensuring that the models which are developed, they don't have any bias. So maybe you're not very familiar with this. Like currently there is more work on India also, but like a couple of years ago, the face detection models which were developed, they were primarily developed using data sets based in the US, and in the US the population skews much more white, which is European American, than people of Asian or African American descent. So the models are biased, they were biased much more to those points, and the face detection model would work much better on the people of European ethnicity than people of other ethnicities. So things like this we don't want. So we want the models which are developed to be relatively free of bias and to be working to benefit everyone. Okay, so this is like a more mathematical notion of what is happening. So modern machine learning system, it usually converts each data point into a vector. So in your 11th, I assume like all of you have finished your 11th. So vectors you must have seen, right? In your physics. So in physics, what you see, what? Any question? So most of what you might have seen is like either two-dimensional or at most three-dimensional vectors. So, but you can generalize that to higher dimensions. So basically, you can take like any arbitrary number of dimensions and scale it up, and the loss will remain the same. So a vector is just essentially this thing, quantity with a direction and a magnitude. It's just that the direction can be high dimensional. So I mean, it might not be easy to, not easy, it is actually not possible for us to visualize things which are in higher than 3 dimensions, because we only deal like naturally with 2 and 3 dimensional data, but the same mathematical concepts essentially translate to higher dimensions. So given any data like image, text or audio, so we take this data and pass it through something which is known as a embedding model, and that will convert it into a single dimensional, not single dimensional, like a d-dimensional point. So the data itself, it might not be continuous. For example, if you look at text, so text is very discrete, right? Like you'll have some particular word and like some paragraphs, and then you'll have repeated words and so on. So it's actually not directly like some numbers. But whereas if you want to deal with anything which a computer doesn't understand fundamentally like what is a image or text or audio. The only thing it ultimately sees is zeros and ones. So you want to convert all of this to zeros and ones, but not just that, even the particular nature which I said earlier, that if you look at points which are encoded by these models, the points which are closer to each other, we want them to be similar, and the points which are farther apart, we want them to be different. So that property is encapsulated by this embedding model. So you take this and pass it to that, then you'll get such a thing. And yes, nearby vectors should represent semantically similar examples. Semantic just means meaningful. That's it. So this is an example. So like a text example. So suppose you have a bunch of short documents. Actually here it is about words, but if you see these different words like dog, cat, animal, shelter, kitten, whereas this pizza, pasta, recipe and so on. So if you pass these things through that embedding model, you get a d-dimensional vector, and that d-dimensional vector further, if you reduce a dimension into 2 dimensions, then you will get data like this. So this is like an actual like data which you can generate. And if you see, then all the words which are related to this class pets, they'll be close to each other. Same for food and same for sports. Okay, so what exactly is distance here? I mean, already like you have seen in physics the like 2-dimensional thing, right? Like what is distance? You have this velocity. It's essentially the same thing, except we are generalizing this definition to higher dimensions. So if you have any 2 points which are in d dimensions, so this x will be a tuple of like points x1, x2 until xd, where all of these are just some real numbers, and similarly y will also be like y1 comma y2 comma y3 until yd. So if you have these 2 points, then the distance between them, it's known as this Euclidean distance. This particular distance is just a generalization of the standard distance which you see in 2 dimensions. So you just go from all the dimensions 1 to d, you just take xj minus yj square, which is the same thing like if you have 2 dimensions, then you have this Pythagoras theorem, right? A square plus b square, that is the length of the hypotenuse. The same thing, just generalized to higher dimensions. And this is one notion of distance. Another notion is other like simpler thing. It's just defined as a cosine similarity. So already like you might have seen dot products, right? Like in physics, if you have momentum is equal to the dot product of mass and velocity. So it has a direction. So similarly here, if you have any 2 vectors, then you can compute the cosine of the angle between them by using this formula, inner product of x times y divided by the norm of x times norm of y. So this is a simple thing. So if you have 2 vectors which are identical, then what will be cos theta? 1. Yes. So if you have identical vectors, this cosine similarity will be equal to 1. Whereas if you have let's say 2 orthogonal vectors, then what will 0? Yeah, I mean cosine similarity is like -1 and 1. So probably like if you have opposite directions, -1 might be the most dissimilar point. But yeah. So anyway, so this is another notion of similarity, and this Euclidean distance also is like another notion. So you can use both of these things. Okay, so let's say that you have this data, and all of this, for example, corresponds to some newspaper articles. Okay, the newspaper articles are sent through that model, then they are converted into some d-dimensional embedding, and then further we are reducing the dimension to 2. And now if your task is to like let's say select some of this data to send for review. Like let's say a newspaper is initially collecting a bunch of articles, like let's say it collects 100 articles, and then it wants to select some data which will be read by the newspaper editors, and then they will review them and then select. So how do you select? Like let's say you only have a budget to select 6 examples. So how do you think you can select? And notice that like here we are actually giving this colored things, but before you send it, you might not even have the colors. So if you just have to select, then how do you think you can select? Right. So you choose one point, then you choose like another point which is farther away from this point. Okay. Right. But assume that you don't have colors. Like if you have colors, then let's say you can use that algorithm. But let's say for now that before you send it for review, you only have the points without the colors. Huh. Huh. Uh-huh. No, but now I'm just asking you for a way to select. Huh? What somebody was. Okay, so there is no origin here. Huh. We can define? Okay, sure. Let's say you define your origin here. Then how can you do regression? Huh. So actually regression is for data with labels. So here there is no labels. It's just a data point. So regression is if you have like let's say a two-dimensional thing where one is a feature and other is a like label like you know some I don't know height of a person versus the weight. Then you will use regression like if you want to compute a relationship. But here you don't have that. Here you just have points which are both like you know height comma weight pairs. Uh-huh. Okay. Okay, if you do that, then let's say this is the origin. Then you will just select this, this, and this. Or let's say there is a bigger problem. Okay, let's say that there are a lot of points which belong to this class. Then your mean will lie much closer to this class, and all the points you select will be belonging to just this class. No, but wherever you select your origin, the points which are closest to that can all lie in the same class. Huh. 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 Yeah, that's a very reasonable algorithm. So basically all of these are different types of algorithms. So the exact procedure in which you can select. So we will discuss like one particular algorithm you can do, but all of them are like somewhat reasonable. No, also I think somebody said you can randomly select the points, right? So there are some issues, which is that if you select points randomly, then if you have too many points belonging to the same class, then even when you select uniformly random, you will end up choosing like too many from that same class. In the case of like this patients which like healthy people and people with a disease, like if you randomly select people, then you might have much more people belonging to the healthy category, which might not be that helpful. Okay, so a good subset, like one of the properties of a good subset should be that it should cover the entire map, essentially like some type of notion which you said, like if you draw some circles with let's say some fixed radius, then other points should like belong in that. And also another property is that it should not ignore rare regions. There should not be any points which are like left. Okay, so essentially this is like captured by this notion called as clusters. So a cluster is a group of similar examples, and a representative for a cluster is like one point which stands as a representative for all the points in that particular cluster. So for example, here, let's say that you have decided that these three are the different subsets, and then in this subsets, let's say you select one point each, which are the representatives of these subsets, then you can label those representatives, and you will learn a lot about the data set. Yes, so now this is like an intuitive notion of what you can do. So now we want to mathematically formalize how this can be done. Because if you want a computer to do anything, you need to give it very concrete instructions on what it has to do. You cannot just explain like in vague words. You need to give it very concrete directions and a mathematical formulation for it to do something. So particularly the notion which we will use is this objective function known as the k-means objective. So what is this objective function? So if you have like n points, n data points, each in this d dimensions. So we want to choose k centers, C1 to Ck, also each of them in d dimensions. For now, for simplicity, you can think that these are all belonging to two-dimensional plane, but this is in general, it is relevant even to higher dimensions. So in that, for every data point, you will assign the data point to its closest center among the chosen centers. So that will be the representative for that center, and the cost which is associated with that data point. So the closest center is just this function, the minimum data point from 1 to k, which will be the closest to that. And then the cost is a square of the distance between the data point and the closest center. So essentially every point pays the square distance to its closest center. And if we can label, let's say, k examples, then all the centers which are chosen are the natural candidates. Yeah, so also like this particular way we have described, the centers need not necessarily belong to the like actual data. The centers could also be like arbitrary. But if you further constrain this problem where the centers must belong to the data, then that is known as medioids. It's just a different term. Instead of means, it's called medioids. Okay, so this is like a very famous algorithm. It started in like, I mean, it's a very intuitive algorithm since 1950s. This is popular. So in this algorithm, I think actually someone was describing basically this algorithm. I don't remember. Was it you? Do you already like have you seen this before? Okay. So was it discussed today in any class? Okay. So you start with basically k centers. So these can be arbitrary centers, and for each center you will assign basically among the entire data set, you will assign each point to its nearest center, and then you will get like some k different classes, and then for the clusters which you found, you will compute the mean of the cluster and then take that as a new center, and then you will keep repeating that until there is no more movement. Like we will describe like example. Okay, so let me see. Yeah, this is just like, I'm not like choosing this for any particular reason, but this is like a popular thing. You can just search and there are a lot of examples. So here, let's say these are the different points which are there. Okay. So these, let's say this is like the final thing you would want, but when you start with the data, this is not existing. And the concept which we described earlier, if you take 2 points which are close to each other, you want them to be similar. Farther apart, they are less similar. And the centroid is the mean of the different points in that cluster. Yes. Okay. So initially, you will start with selecting some random point, like let's say 1 point. Let's say this is selected as 1 point. And let's say that these are the other points which are selected. Okay, let's say the initial 3 points which you select are these 3 points. Then using these 3 points, you will compute these partitions. So these things are known as Voronoi partitions. Voronoi is just like some Russian guy who came up with this thing initially. So then using them, you will get these partitions. Like between these two, you will compute the perpendicular bisector of that line. Similarly, even between these two, the perpendicular bisector, and between these two also the perpendicular bisector. Essentially, if this is a triangle, then these will all be the perpendicular bisector of the sides. And now you will first assign like all points here to this blue cluster, all the points here to this green yellow one, and then the ones here. So this is like a first step. And then you'll use that to now color these points. And then once you color these points, now you will compute the mean of these points, like the blue points and the red points and the green points, and you will move these centers to the means. Yeah, this update centroid step did that. It moved it to the means. And okay, so now this is basically stable. Like once you get this, now if you do a clustering again, this will not change the clusters. The same clusters will remain stable. Then again, this will go to the final means, which are the centers of these groups. And then once you reach here, your algorithm stops because there is no need of doing any more of these steps. So that is an algorithm. Yeah, so this is the algorithm which we discussed. So earlier I said that like initially you choose some points and then you keep doing this process, right? So obviously like you can start with some random points, but there is a smarter way to choose them to ensure that your algorithm converges quicker, which is that you first select the first center uniformly at random, and then using that center you compute the distances to all other data points. Let d of x be the distance from that point to the other points. Then you choose the next center with probability that is proportional to the square of the distance. Okay, so this ensures that faraway regions are more likely to be chosen next. So there is advantage of this, which is that earlier you have seen that like you start with some position and then you keep moving to a final like state, right? So if you start with a better like more diverse selection, then you will reach quicker to that final optima, and also you can like get overall better quality of these clusters. Any questions here? Okay, so like this seems like a harder thing to implement, right? A simpler thing would be if you start a point, then you can select just the point which is the farthest. Why do you have to select this randomly according to square distance? Why do you think, what might be a problem with that? Uh-huh. Right. No, but the other option where you select only the farthest point, that can also be an algorithm, right? Like you select one point initially at random. The next point you can select is the farthest away from that. So why do you think like this is the standard thing which people do in practice? So why do you think like this is preferred over that? Maybe like what could be an issue with that? No, computation is the same time. Like even to run this algorithm, once you select a point, you need to compute the distance of every point in the data set to that point, which is the same even if you want to select the farthest point. So it's the same time to compute. Huh? Unfair grouping if you choose only the farthest point. No, I'm saying regular K means initially you choose random points. So that is anyway that's a bad option. Like just because if you have one class with too many points, like let's say your distribution has like 10,000 dogs and only 10 cats and 10 ships. Then if you choose all at random, then you might miss everything. Like only you can choose cats, right? So that we don't use in practice. This is the one which you use in practice. The question is, why do you have to do this random sampling and not just pick the point which is the farthest away? What could be a problem with that? Yes, yes. So in a case where let's say so the points which are far away from most of the data, they are called as outliers. So outlier means the distribution of that is different from the typical point. So if you choose an algorithm where you always end up choosing the farthest away point, then your data, the choices which you pick can be too skewed towards the outliers, which you don't necessarily want. Like you want a balance. Like in the case which I described earlier of let's say 10,000 cats and 10 dogs and 10 ships or whatever, you don't want to have the case. I mean, if you want to select let's say 100 points, then maybe actually you want more points from this cats also. So this does a balance. It balances between the case which is taking all the points uniformly at random and the case where you are choosing the farthest away point. So in practice, it turns out that this is better than both of them. And your algorithm is not too sensitive to outliers. And outliers can be for any random reason. Like suppose you are collecting a data set, like now the Indian census is happening, right? So let's say somebody is collecting the census data by going to each household and recording like some items in the house. And it can be the case that a person who's entering, if they are collecting like let's say 1 crore data points, then due to some data entry error, they collect like some wrong data due to whatever reason. So then those will be the outliers. So if your algorithm is too sensitive to outliers, then your final result or whatever you want to do might be bad. Okay. So this k-means algorithm which we described, that is not the only way to do clustering. So usually those things are known as centroid based clustering algorithms. There are also other algorithms which are known as density based algorithms. So they go and compute the, so here the density is essentially the same concept which you see in physics and chemistry, except that there you only see for like whatever 2 dimensions and 3 dimensions. Here suppose each of these points has some mass, let's say uniform mass, then area with higher density will be points like regions with higher points. So there are some things which also work on the basis of that for clustering. And this is a standard pipeline for doing this text clustering. Like if you have some documents, so like suppose you want to read about a particular topic, something which you are studying, right? Like about some topic in some physics or biology or something, and you have read from your whatever textbook, but you want to learn more about that topic. So now if you just search online, you will find like 10,000 different articles about that topic. But let's say you only want to read like a couple of these articles which are different from each other. So then this can be a pipeline. So you take all those documents. I mean, you don't probably do this with computers right now, but it is an approach. You can take those documents. Since it is not possible for you to first read all of them, you can just send it to this large language model, which can generate these embeddings, and then embeddings will be in D dimensions, and then you run it through another algorithm which will reduce the dimension into some whatever smaller number of dimensions, and then you can run this k-means clustering algorithm which we described, and then it will cluster these documents, and then you can select whatever is your budget. If you want to only read 5 articles, then you can say I only want 5 means if you run it. So then it will convert them, and then it will give you like out of this let's say 10,000 different books or articles, it will select the 5 most different and interesting articles which you can read. So then you can go and just read those articles, and they will give you the most information for your time. Yeah, so we want to reduce the dimension because typically these large language models, the dimension which is directly you get from the embeddings, it can be hundreds or thousands of dimensions. And if you want to directly like look at them, it's not possible. So you want to reduce into like let's say 2 dimensions or even small, like 3 or 4 or whatever. Okay, so actually this topic, okay, this topic also let's discuss. We have some time. So there is another notion which is very useful, which is known as topic modeling. So topic modeling is if you have a set of articles, basically a set of text data, without actually like manually reading through that text, let's say you want to get some information out of it. So for example, if you have this cat, dog and kitten, let's say that is like one cluster of words. Another one is pizza, pasta, I don't know what is this. And then the soccer, cricket match. Then instead of you having to, actually go and read these things, suppose a model can automatically figure out, like, that, okay, this belongs to the topic of pets, this belongs to the topic of food, and then this belongs to the topic of sports. It can be a very useful thing to have. So this notion of topic modeling, what it does is, eventually after you select your clusters, then it will go and summarize each cluster, like what is that corresponding to. So this overall, it belongs to this class of like this object, this topic which we know as natural language processing. It's one subfield of artificial intelligence. So here, if you have a bunch of documents, which is basically in human language. So human languages are known as natural languages, to distinguish them from computer programming languages like C, C++, Python. So from this natural language, if you want to find the topics, so standard representation is known as this bag of words representation. So if you have each document, first you will create this table where the number of columns will be the size of your dictionary. So if, for example, you are only reading English documents, so then you pick, like, let's say some Oxford English dictionary that will have some finite number of words, some I don't know, 20,000 or 30,000. So then you'll create like 20,000 columns, and for each document you will go and you will find out how many number of times like one word is occurring in that document. So this is a very natural representation, right? Like if you look at this doc 1, maybe it has like one occurrence of cat and one occurrence of cute, and then like a bunch of other words. Similarly, this document 2 could be like one occurrence of dog, another occurrence of cute, and then other one is pizza, match, and so on. So if you have this smaller representation, this makes life much simpler for like some algorithm, because algorithm doesn't actually go and actually read and understand the text. So then once this representation is there, you can convert for every cluster. So okay, so every document we have converted into this bag of words representation. Now earlier we had already formed the clusters for each of these documents, right? So those clusters, you can again find the bag of words representation for the entire cluster. You can just add up like each bag of words representation to find that in each cluster what is the number of occurrences of cat and so on. So once you do that, you can find like a summary. So in each cluster C, you will find the frequency of the word in C. So that is the number of times this is commonly occurring, times this logarithm of all the clusters divided by the clusters using that particular word W. So why do we use this? So let's say that you have a word like a or the, like things like this, articles or other like generic words, we don't want to use that information. We want to essentially throw away that information, right? Because they are like generic words, so they don't give much information. So that's why we multiply. So if you have, for example, like all the clusters are having the word the, then the number of clusters, all clusters divided by the clusters using that particular word, so this will be equal to 1, right? So if this is equal to 1, then what is logarithm of 1? 0. So this frequency will be multiplied by 0 to find a score for that word. So then we'll score it to be 0, because even though some word like a or the might occur very often, because it is occurring everywhere, you want to essentially throw away that information. So only the more interesting, like rare words, like I don't know, if you find some word like white snow leopard, then maybe that snow leopard is a very unique object which might only occur in documents about animals. So snow leopard, maybe you'll not see it in other articles about, let's say, food. So we will score all the words using this both the frequency and also this rarity. This particular thing is known as this CTF IDF, where this TF is known as a term frequency, which is just this thing which you see. So the number of times the term occurs in the cluster, that is known as term frequency, and this IDF stands for inverse document frequency. So it's just the inverse of how many times, so document frequency is just the clusters using W by the all clusters is the inverse of that. So the CTF IDF stands for C term frequency, inverse document frequency, to score the words. Okay, so this, so this is basically a entire pipeline for how you could use this ideas which we discussed today to like achieve some concrete goal. Like if you have some, let's say, project where you are supposed to write a report of all, I don't know, find some topic. Like if you have some project where you have to write a report on I don't know, what are the things which you get as homework, something. You don't get any homeworks to write reports because all the questions are MCQ questions. Okay, so let's say you want to study volcanoes. Okay, like I don't know whether now you want to study, but at least when you are in your 6th or 5th class, if you want to read some encyclopedia, volcanoes or dinosaurs. Okay, so that's an interesting topic, and let's assume that dinosaurs are not very well studied in your textbook. So what you can do is you can find this thing. So you can find all the documents which have dinosaurs, and then you can run them through this large language model, and you can find the embeddings which are in some high dimensions. Then you can reduce the dimension, then you can cluster, and then once you cluster, you can use the earlier discussed this CTF IDF to represent the topics by finding the most important keywords of those topics, and then you can use some other algorithm to rank the importance of those keywords, and then you can get a list of like whatever 5 articles or 10 articles. So it's like an entire pipeline which you can use. Okay, so what we discussed, it also is closely related to the topic we started out with, which is if you have a small budget, then what can you do? Essentially, like once you find this representative topics, you will ask a human to label that thing. And this is not the only approach, but it's a strong baseline. So for each cluster, if you have 1 or more labels, then it means it's a good coverage of the data set. Okay, this will actually skip, like it's, let me, yeah. Okay, so because this is like a research showcase, what I wanted to just like let you know is that a lot of the things which we discussed, these are actually like active research topics. So typically, like in computer science, what we do is there is some concrete problem which we want to solve. So that concrete problem you will define mathematically, because if you don't have a mathematical definition, there is nothing the algorithm, like computer, can do. So once you define that problem, then you want to solve it as quickly as you can. So typically, a lot of these problems, if you want to find the exact solutions for these problems, it is actually impossible to do it within the like time you have. So for some of these optimization problems, if you want to actually find the the exact smallest or the exact largest objective achieving solution, it can take time which is larger than the number of atoms in the universe. So for example, if you want to like, you know, develop a chess playing robot, then given if you start from some point, and if the robot or whatever program has to decide like which is the next best move to select. So actually like, you know, selecting the exact best move, it will take too much time even for this 8x8 chessboard. So then it will try to do some type of approximation. Okay, I don't care about choosing the smallest or the highest possible value. I'm okay with like, you know, some, if it's like okay, like better than a random choice, then what can you do? Then you'll choose something. But these are all again like active, how can you do even better than what is currently there? So that is what is research. Like you start with some problem, and then you see what is the current existing approach, and then you want to learn how can you improve on that approach. Yeah, so so this is another interesting area which is known as active learning. So earlier the way we discussed, like we are algorithmically selecting the best points to label, right? But actually model itself can ask questions to a teacher. So just like all of you are students, and then you have your teachers who are there to teach you. So if you have some model, like let's say GPT-5 or something, then so in active learning, so that model itself will give you like, basically there will be some human who will be sitting there, and then the model will be doing some type of computation, and then when a model realizes that you know, like some examples are confusing to it, that will ask a question. So you know, if like it has like 10,000 images and initially some of them are labeled, then the model is trying to do some learning on those images, and then it goes and finds that, you know, there are these some images which are confusing to it. It is not sure what these things are. Then it will give only those images for the human to label. So that is the approach known as active learning. So yeah, the human is there, but the AI model is also like learning. Okay, so this is like sort of a summary slide. So labels are often the bottleneck in machine learning, not necessarily raw data. And embeddings turn examples into some geometry, which is this high dimensional points, and clustering finds structure in this unlabeled data, and topic modeling in the case of documents like natural language processing, it helps interpret these clusters, and subset selection, it balances all these different notions which you care about, like coverage, diversity, and uncertainty. And broadly responsible AI, the question is, if the budget is small, then who is missed? So the like people or the topics which are missed, if they are more sensitive, then you want to make sure that they are covered. Okay, so that is presentation. Yeah. Any questions? Okay, thank you. Hope you learned something useful. And these are all like public topics. You can just look them up on Google and learn more about them.